Okay, morning everybody. Let's get it rolling. So this is going to be the second lecture of solution theory, and we're going to specifically talk about entropy of mixing. So the goal of today's lecture is help everybody to understand how to interpret how much entropy we have gained when we mix in two solutions. Okay, and you guys see I brought a teaching demo, so we're going to play a little with these solvents. They're blue color and they're red color. Perfect. And in the first lecture, let's quickly recapture what we have taught in the last class. If everybody remember, last time we reviewed thermodynamics, we discussed how thermodynamics is very important in understanding if you're mixing solvents or if you're mixing polymer, will they prefer to be homogeneous or will they prefer to be phase separated, right? So to understand that, we need to have some basic understanding what is entropy, what is enthalpy, and what is the free energy. So we did a little bit of review of that. What is entropy is related to randomness of the system, and we know entropy is likely going to go up when you mix in things. But to how much degree it's going to go up, we didn't discuss in much detail. So in today's lecture, we're going to talk about actually how much entropy you have gained. We can calculate it. And then we also talked about enthalpy, which is heat exchange when you mix in solvents or mix in polymers. And that's a little bit complex. So we're going to start with entropy discussion first, which is the topic of today. Last but not least, we know how delta G is linked to enthalpy and entropy. And when you're thinking about mixing process, if it mix or not totally depends on the free energy before and after mixing. So you need to know what is free energy before you mix it, which will be thinking about two independent systems there before they mix. That would be a box of solvents A, solvent B, and after mix will be a mixture of two. Okay? So there's the simplest thing we can start is called regular solution theory. It sounds so fancy, right? Regular, but it's not like ultra or pro or whatever they want to call it. But it's actually very, very powerful and useful. This is the fundamental of what we're going to learn in the Flory-Hagen theory. So it's very important everybody lay a good foundation about what is regular solution theory. So first, let me tell you what this theory does. Instead of talking about polymer, because the connectivity and we talked about size of polymer will be bigger than solvents, so it's very hard to understand how the size difference between these two. So why don't we start with something really simple? When we talk about mixing solvents, which is solution theory is, you're mixing two solvent, we assume solvent molecular almost exactly same size, so we don't need to worry about size difference between two mixtures you're going to mix. Okay, that's one good thing. So let's talk about a little bit of assumptions. So this model is very simple, but it allows you to calculate delta G. It also serves the basis for treatment of polymer solution. Assumption 1, the enthalpic and entropic portion of free energy can be treated separately and are additive. What that means is basically you can compute each possible arrangement of the molecular, then add them together. And we will do today. We will actually discuss about how many possible ways we can arrange the molecular. And entropy, we can just calculate how much interaction between moleculars and we can add them together. Basically, when you think about macroscopic versus microscopic phenomena, we can simply add them together. It's basically, it's a simple addition. So entropy, under the rule of static thermodynamics, we can break this in several components. Entropy is related to external degree of freedom. So it's also related to internal degree of freedom, so molecular rotation, etc. And most important, this one is configurational entropy, which is what we're going to calculate most of today. Okay? As you can see, the assumption 2 is it doesn't change. The type 1, 2, 3 don't change a lot in our case, but we're only going to consider the configurational entropy of mixing. Configurational entropy, and some of you might ask what it is. So let's talk about that. Hold on. Let me do it one more time. Okay, looking good. So we're going to use a model called lattice model. So let me first introduce what this lattice model is. And in the lattice model, we basically going to fill a given volume and put the molecular there. And think about here, these are our 2D, two-dimensional. It's just a planar structure. You can see we are drawing a lattice. So this is a hexagonal, triangle lattice from a hexagonal grid, right? And this is also a different type of grid. You can see each molecular has different neighbors. In this one, if I put a red dot there, this red dot has 6 closest neighbor. So it has a lattice, it has a lot of neighbors, so lattice has more neighbors. And we can see different ways you can pack. Instead of 6, we can have 4 or 3 neighbors, depends on the different lattice. So this different lattice model will result in different outcome. But for the simplicity of our discussion, for today's calculation, we're going to start with something really simple. Let's start with the grid model. Let's have a 3 times 3 grid. Okay, in this case, we can fill 9 solvent molecular, right? So you can imagine I can have 9 solvent A, and I can have another grid representing another solvent B. Let me try to use the red color so that shows the difference. So if I have a different solvent, I can again have a similar amount. In this case, we're using a same amount solvent, so A and B, which can be represented by this gonna be our solvent A, which can fit in each lattice, and this is gonna be the solvent B, fits in here, okay? So let's finish this slide. So different lattices will result in different interaction pair. Particularly when we calculate the enthalpy, it matters a lot because enthalpy is related to molecular interaction, right? We talked about enthalpy is related to heat exchange when you have molecular come close or go apart. So it matters how much neighbors you have because that dictates how much energy exchange you will have. So if you have 6 closest neighbor versus 12 closest neighbor, it will impact how much energy exchange when you remove one molecule or put it in there. Okay? So this is what these closest sites. In our case, we're going to choose m equals to 4 because this one represents each one has 4 closest neighbor. Because we have limited space, we're only going to draw 3 by 3. But imagine when the lattice is much bigger, maybe 10 by 10 or 100 by 100. So each dot should have 4 closest neighbor in this scenario. Okay? So the last assumption that we will talk about is when confined to consider a configuration entropy, there's no energy difference. Having A type versus A or A type next to B in this scenario. There's no configuration entropy in this case. It's only related to where we put them. All right, so this is going to be a little bit complex. So first, I want to tell you how to calculate entropy. So entropy is given by this equation. It's defined by Boltzmann definition. So S, entropy is related to K. K is a Boltzmann constant. So this is a value that is known and won't change. All right? So, and lowering omega. So if this is a fixed, your S will be a function of omega only. So it's, it's not that complex, right? If you only have relation to omega between entropy, we should just calculate what is this omega value. And let's define. Omega is defined as number of microscopic arrangement compatible with the same macroscopic state of system. This is really a mouthful. But it's basically say, if I have 9 possible grids we can fill in, how many different states we can have? So omega is number of different ways you can fill the lattice. It makes sense, right? When you have a lot of different ways to configure your lattice, that means you have a large entropy. Example would be you have mixed system. When we have the mixed, we're going to mix them together. This is not equal volume, but you got the idea. Now we will have the different red and black color. They will have a lot of different ways to fill it. So in this case, when we start off, what's the entropy for the system? So this will be, before we mix, all right. So now I'm going to pick a few blue ones. It should be 9. So how many different ways I can configure those 9 blue molecular on this 9 grids? The first one you can fill anywhere, right? But eventually, once you fill 9 cross, does it matter which cross I put first or second? Doesn't matter, right? There's one uniqueness is each of them are identical. So the entropy of the molecular, before we mix, we can conclude this will be only one simple configuration is molecular X is on each box. That's the entropy before we mix it, okay? So that's for molecular A. What about B? We have 9 of them, and we have 9 available spots to fill them. So what the entropy is the same, right? We would have to fit each molecule in each lattice it need to go. There's no way I can say, hey, I want to change with you. Will there be any difference? No. So if we apply what S, ln K ln 1. What is ln 1? 0. This will be equals to 0. Same for this case. So before we mix any solutions, we have no entropies at that state according to this table. So our delta S, entropy change once we mix them will be equals to S after mix, right, minus S before mix. And this value we know is equals to 0 plus 0. So this would be the state here. So now I'm going to ask a very difficult question to you guys. We got 9 different moleculars. We're going to fill this lattice. how many different ways we can fill it. So let's do a simple experiment together. Then I will give some time for everybody to think a little bit. Pick one, a random. Pick one. One is dark, the other is milk. Pick one. Everybody likes dark chocolate, huh? And Sarah? All right. And I want everybody go up and fill a spot that is not filled. Okay? So you guys can go up. Remember your color. If you're blue, pick a black pen and draw on the board where there is 3 by 9 lattice.
It's 3 by 6.
3 by 6, right. There's left. Okay, let's start with the first student. Let's go one by one. Chris, then you can finish the chocolate.
Sure.
Okay, so I have 3 red. Okay, let me draw first the 3 so I don't forget. Okay, now you guys can feel whatever way you like. And while you are feeling the different spots, try to build random. Pick your spots where you like. Okay, good. Okay, so while you feel the different spots, I want everybody to also think how many different ways we can configure the box. So once we are done, we should have just the one way we filled it. That's what this time. If I let everybody do it again, erase it, it will be a different configuration, right? So the question is, how do we understand how much randomness is there? Remember your color, okay? I don't want to see 10 cross. That will mess up the lecture. We should have 9 black, 9 circle. Okay, good. Keep going.
Megan, don't take my spot. Take a spot, Megan.
All right. I want everybody to remember roughly where you feel, then we can come back to calculate it.
Is that your spot? No.
Okay. Let's have Jamie.
The other corner?
Uh-huh. So how many possible ways we can fill? It's going to be a lot, right? Imagine every student has different ways to fill it. So at the end of the day, we want to calculate how much.
Good job.
Sorry.
You know, as soon as you said that, all of us desperately wanted to take your spot.
So, well, if you can see while we start feeling it, the leftover spot is getting less and less. You know, when it left to Daniel, he only had 1 available spot, right? And the only one. So the question is how many different ways we can fill it. And it cannot be repetitive. It needs to be unique ways to fill it. Okay, we have 1, 2, 3, 4. Last 4. Almost there. Almost there.
I have a question. On
Yes.
The first 2 that we did, would we ever have like 8 solvent error, or would there always be 9?
It will be 9, because that's what lattice we want to just prescribe. 1 molecular has 1 lattice to it. And then when we mix them, we're going to add more lattice.
Okay.
And we assume there's no volume change in the mixing, so it simplifies things. That's why we have from 9 lattice goes up to 18. All right, last 2. All right, it's good. You can walk a little bit, stretch, right? So, all right, let me count. 8, 9, I think we should be right. Yeah. Yes, you are right. All right, good. So we now fitted 1 out of many ways we can think about molecular with a mix, right? That would represent 1 way. If I shift to this red and this black cloth versus the red, they're going to change configuration. So imagine I have just to put that in a box, I shake it, it will likely to be a very different configuration. So that means the entropy in the mixed system goes up, because this represents phi, one of many phi, one of many omega that we discussed. If we change it, so the question for today is, how do we compute how much omega we have? It's going to be big. I think it's going to be more than 20, or maybe over 100 different ways, right? So anyone have any idea how we can calculate how much configuration we have? Well,
Did you do the factorial?
But then how do you tell which ones are the same? Like, how do you take account for ones that are the same if there's only two components? 'Cause
Yes.
factorial would be like if each one was different.
yeah.
Use the denominator. Just like that.
Stop looking at it.
All right. So Joseph, you think that's very good handle. So tell me about it. How would you approach this problem?
You would take you want to do the factorial of all the possible spots. Which
Okay.
is 3 times 6.
So that will be 18 factorial.
But then, like Amy said, you have to account for each kind. So you have to divide by 9 factorial and 9 factorial.
And explain why we need divide 9 by 9.
Because as you start putting them in there, you have less of one or the other.
Close. So let's go back. I think your direction is very correct. Anybody is not familiar with factorial? We can talk a little bit about that. So factorial, let's use smaller number. Factorial is basically equals to 9 times one number smaller times 8 times 7 times 6 all the way to 1. So this is going to be a very big number, but let's do a full factorial because this will be easy. This is going to be 24. Of course, there's times 1, but it doesn't make a difference. So, okay? And the factorial, why we want to use a factorial to consider how many different ways we can calculate different configuration.
Because when you're filling the first box, you have 16 total things, and then
Yeah.
filling the second box, you have one less.
Correct. 18. The first person fill it would have 18 different spots they can put randomly. So if we don't consider, let's assume each of them are unique. Each chocolate just 18 flavors. Then when you put in this box 18 different flavors, you can achieve different ways you can put it. The first box person put in would have 18 selections. If the second one put in, because the spot is taken, so the second one would only have 17 slots to put in. And last person only have one last spot and kind of stuck with that. Sorry, Daniel. Next time we go the other way around. Let's be inclusive. So everybody understand now what is a total number, but like Amy said, there is a repetitive number because we only have 2 colors. So even we put this first, the second, if we switch it, put this first, this second, they're the same, right? They're both red. So we need to take out what is repetitive for the red. So we need to divide by how number of red we have repeated. So how many number of red is we just need to consider the red? Because, if the first field is red versus the second field is the same, so we need to consider there's a repetitive way we're going to, I should not use a black color. It's in red. So we just need to consider how much repetitive we could have while we fill out all the red. So we can count. There's 9 of them. So if I fill this first, this second, they're the same. So we can divide by 9 factorial, which is this one. And we can need to divide again, or the repetitive black, which is given by 9 factorial again. So that will give you the right answer. So can someone help me calculate it before?
Oh, I was just wondering, like, how do you know it's 9 factorial, or I guess m factorial? like component factorial.
In this example, it will be 9. But if you mix in two random number, let's say m molecular A and m molecular B, it will be generalized by n1, n2 factorial. And this is combination of n1 plus n2, so the total number factorial, okay? So if we imagine our case would be 9, 9, this would be 18. 9 plus 9 equals to 18. So can someone help me? Oh, this is too long.
It's,
I'm curious.
Oh, how many spots?
No, how many omega we have?
Oh,
It's going to be
48,620.
48,000. Okay. And how much?
620.
620. So I'm glad we didn't ask everybody to keep trying. That will take the whole semester before we figure out the total. But if it's just a box and a box of 4, that will be easy. Let's do a quick one for a box of 4. So if we mix 2 molecular red, or just call it A, 2 molecular B, we would have reached a conclusion it will be 4 factorial divided by 2 and 2. So this will be 24 divided by 4. It should be 6 different configurations. Oh, there's a question, yes.
All right, so what if you have that 4x4 box, and then you have like more than 4 things you're going to put into it?
Oh, that's basically what lattice says. We're going to have equal number lattice. So each solvent molecule occupies a lattice. And it's in the later part when we talk about polymer-solvent mixture, the polymer will occupy a slightly more lattice. So we will get into that. But there should be 6 different configurations. So let's see if we can figure out quickly those 6 different configurations. What are these? Let me. Okay. And they cannot be repetitive. All right, let's start with Daniel. Daniel, can you help me do a random configuration?
sure,
Where you want to put it? Just tell me where the reds are.
in the top row.
Okay, so we have 2. Let's jump 3 students to Winfield. How about you?
If you, I guess, do like red, blue, red, blue.
Red, blue, red, blue. Okay, let's jump 3 students and Jen.
Okay, so the first row is blue. The second row is
Okay, that should work, right? It's non-repetitive. So how about we have buka, right? Yeah. What's the possible way we arrange it?
Second row,
Let's put the second row what color?
red.
Red. And how about this one?
It's blue.
Okay. So this is new. And how about the top 2? Do you have a preference?
The white one.
Same, okay? No, we have to reverse it. Otherwise. So this will be new configuration. It's getting harder. So Megan, you can take the last one. I'll take the last one.
The left side with the X's and then the right side with blues.
Left side is this way. All right, so it should be 1 left. I guess it's going to be the symmetry of this one. Right? Okay. So this will give you some idea. But when the molecular start to go up, it's very hard to count them manually. So we discussed about how we can calculate the number of total different states. So this is generalized. In this example, we have 8 by 8 instead of 9 by 9. So we have 16 slots. M is number of white beads, and M, red, is number of red beads. This M means total, so total available spots. So number of ways we can fit in every single site would be M factorial Now you think about number of possible way fill in those. y1s will be 8 m1 factorial, and this will be n2 factorial. So total of way we have discussed it will be omega equals to total number of lattice divided by white lattice and factorial and red lattice factorial. Okay, so this gives you the omega.
I assume for anytime we get more solvents or whatever, we would just add another denominator factorial if we did like 3 mixing things.
Good question. I never thought about that. Yes. In the 3 mixing phases, it will be total number divided by 3 different color because we are indistinguishable within one solvent. That's totally correct. But in our lecture, for now, we're just going to talk about binary for the simplicity of the discussion. Okay, so you guys made a big step today. We solved what is the entropy of mixing. So we can get what is the entropy S will be K ln omega. And we know the omega value in here. We can get after mixing what is omega is, right? So we can get delta S will be K ln omega minus 0. So there will be a net gain of entropy. When you mix, an entropy goes up.
Did you say what the value of K was? I know you said it was a constant, right?
Say that again?
What the actual value of K is?
I can look that up. It's a constant. I can memorize it, and in the exam it will be giving on the equation sheet the specific value. Okay, so this week kind of talked about what is the entropy differences before we mix them. So, everybody has any question for the orange box? Any question? So this one we have covered, right? We talked about how entropy relates to number of different states, and we calculate different states is related to total number of molecular divided by M1 divided by M2. So we're gonna do a little bit of simplification. Instead of lawing this long bracket, we're gonna do something to simplify this equation, and there is a little bit math here. So let's talk a little bit about conclusion. The ln m1 divided by m1 n2 will be equals to this equation, m1 plus n2 ln m1 plus n2 minus m1 ln m1 blah. So we will explain how we get there. That's important. So we're going to use this Stirring's approximation because factorial in the equation is hard to treat. So we're going to eliminate factorial. When n is very big, log n factorial is approximately n times log n minus n. So we're going to leverage this knowledge and just plug in here. So let me walk you through. Log m factorial divided by m1 factorial, m2 factorial can be simply rearranged into this equation because log on the bottom of this equation gonna have a minus sign. So using the equation, we can expand the first part. Log n will be equals m times log n minus m1, no question. And the second part will be m1 log m1. And minus m1, we're going to change the sign to be plus n1 here. And same for that second half. So now we can cancel out a few terms because this part, n1 is equals to m1 plus n2. So all of those 3 terms just to cancel out each other. We don't left any non-log component. So this is gone, and this is gone. Now, how about this part? We're going to expand to what we have told you, that m equals to m1 plus n2. So this is what this part is, and log m is expand log n1, n2. So this part, what on hand is pointing, is exactly this simple equation. And we're just going to minus this and that. And this is exactly what we show here. One more step. We're going to break this bracket, make it m1 log m1 plus m2 minus m1 log m1. And you might ask me why? Because this allows us to do one more rearrangement of equation. Let me write right here. So we can write equation as n log m1 plus m2 minus m1 log n. So because they both share the m1 term, right? So we can do one more thing, is this would be equals to m1 bracket it's nothing fancy plus n2. So, well, there's one more step we can simplify this part. Oh, did I write it incorrectly? Yeah, this should be log m2. My apology. We basically rearranged it slightly. And last but not least, this can be further, let me use a different color. This portion can be changed into something even simpler. This would be equals to minus m1 divided by m1 plus n2. Right? So what is this m1 divided m1 plus n2? This is basically the volume fraction, molar fraction. So how much number of 1 in the total number of lattice? In the case where we have equal number of mixin, this will be equals to 0.5. So we can define a phi would be, phi 1 would be how much volume, number fraction, not volume, number fraction. If each lattice is the same volume, then you can interchangeably use the number fraction and volume fraction. So in this case, they define x1, that's the same. So x1 will be the volume fraction. And we can see what started with a long equation actually ended up something really elegant. So the entropy of mixing will be equals to minus m1 times log x1 plus m2 log x2. And let me say one more time. M1 is how much number in lattice. So in this case, M1 will be equal to 9 in the exercise we did. So 9 times log x1 would be 9 divided by 18. In our example, that would be 0.5. Plus n2 would be 9 again. Log x2 would be 0.5. So it's very symmetric. It's basically m1 times log x1. m2 times log x2. That would be the entropy. And before mixing, S1 and S2 would both be 0. So delta S in the mixture process is just going to be what we have shown here. Very simple, elegant. I'm shocked when I see this. What? It's this simple, delta S is related to volume fraction and number of molecular, that's it. Okay, any questions so far? So that's basically the in the mixing, what the entropy change, delta S in the mixing, will be related to if you talking about mixing 2 beaker instead of 9 molecular, because that's